Morning, everyone. This is a great pleasure. It's a great pleasure for me to address you all. I've been assigned to talk about the Central American monsoon, which is part of the North American monsoon. And just to give you a broader context, um, this is borrowed from a paper from Magana and all, which appeared in 1999, which is showing you the climatological distribution of rainfall across the North American monsoon region. Um, the next speaker is going to talk about the northern part of the North American monsoon, which includes parts of Mexico and parts of United States of America. And I'll be talking about uh, regions covering from Belize and Guatemala down to Panama. And I'll talk more about this figure, which will appear later on in this part. Central America, despite the fact that it occupies only 0.5% of the Earth's terrain, contains 7% of the world's flora and fauna. That means it is considered to be a biodiversity hotspot. It is the center of nature conservation. The wet season is important for agriculture. It is a major exporter of coffee. The forecast at the seasonal scale is absolutely critical for the agricultural yield from this region, and also for water supply and demand measures. The variability of the wet season and the dry season is also critical for tourism, as it attracts a pretty large tourist population. And also, the hydroelectric power requires reliable influx of fresh water, and variations in that need to be known in advance to manage the generation of hydroelectric power. So, from many aspects, it is important that we understand and are able to predict the seasonal to environmental variations. The region, the geographic region of the Central American monsoon region is pretty complex. It's a narrow strip of land connecting the two continents, the North American and the South American continents. It's an isthmus with relatively warm oceans on either side, the tropical eastern Pacific out here, and the Caribbean Sea to its east. The width ranges anywhere from 100 kilometers to 400 kilometers, with a of about 1,600 kilometers. So, Belize, Guatemala, El Salvador, Honduras, uh, Nicaragua, Costa Rica, and Panama comprise the Central American monsoon region. The terrain actually gives a very complex climatology for this region. You have two mountain terrains, uh, which crisscross the Central American region and divides them into the Pacific slope and the Caribbean slope region. And they have quite different climatologies. So if I show you in the context of a detailed topography and bathymetry over the region, this is what it looks like at about 15-kilometer resolution. The Central Cordillera and the Sierra Madre are the two major mountain ranges that divide the region into Pacific slope region and the Caribbean slope region. The ocean bathymetry also has ridges and valleys. Um, and our lab does quite a bit of climate modeling, both of the oceans and the atmosphere. And this is the depiction from one of our regional model uh, integrations over this region. The seven important features of the Central American monsoon are the North Atlantic subtropical high, which is residing over the North Atlantic region, which is outside the domain of this figure here. Um, it has also the meridional migrations of the ITCZ in the tropical Eastern Pacific, the equator-ward intrusions of the frontal systems that periodically intrude into these latitudes in the boreal winter season. The tropical easterly waves or the African easterly waves that make their way into the tropical Pacific, passing through the Central American monsoon region. And likewise, it has been observed that in situ tropical easterly waves are also generated in the Panama Bight region as a result of the tremendous diabatic heating that is released from the latent heat of condensation over this region. There's also the monsoon gyre that develops periodically, um, and also the Caribbean low-level jet and other low-level jets that we'll also be talking about. And then there is this phenomenon of midsummer drought that is somewhat unique to this part of the world. So coming back to this figure that I earlier talked about, um, you can see here the amount of uh, uh, the uh, the climatological distribution of rainfall across these 10 degree by 10 degree boxes, I believe. And you can see that as you come closer to the coastal Pacific slope of the Central American monsoon region, um, you begin to see a dip around July and August. And in the preceding month of June or the succeeding month of September, it rises again to give you a biannual peak in the minimum in July and August. This is what we refer to as midsummer drought, and it is the strongest at these latitudes, and it disappears or becomes diminished as you move into the Caribbean region. Likewise, as you begin to move equatorward, you also begin to see its diminishment or disappearance. And so it is unique to, somewhat unique to the tropical Eastern Pacific of these latitudes. And as you move further up north as well, the midsummer drought phenomenon also begins to diminish. Um, there are many theories that exist for the midsummer drought, which we will not discuss at this point. It has also been connected to variations in the Indian summer monsoon, um, and, um, and there have been theories talking about the meridional migrations of ITCZ also affecting the midsummer drought. If you look at the annual cycle or the seasonal cycle of rainfall along the Caribbean slope, it clearly comes out that they have a biannual peak, one in the summer, one in the winter. They line up well with the seasonal fluctuations of the Caribbean low-level jet that I'll introduce you to in a moment, but it serves as a conduit for moisture supply in the Caribbean slope and provides moisture from the warm Caribbean Sea into this region. The Caribbean Sea serves as a major moisture source over most of Central America, and the tropical Eastern Pacific serves as a secondary moisture source in comparison. In the winter time, the moisture source gets displaced towards the Gulf of Mexico during winter, but over most part of the summer, which coincides with the wet season, the major moisture source is the Caribbean Sea. If you look at the seasonal cycle of the precipitation along the Pacific slope side of the Caribbean, Central American region, we see this famous midsummer drought, and then the peaks of rainfall in June and September. Um, Seasonally, in the summer, humidity transport from the Caribbean contributes more to precipitation over Central America, as I said before, compared to the Eastern Pacific region. This region of Central America is also characterized by the Central America Dry Corridor, which is shaded in this brown color. This is a region that has more frequent dry spells during the wet season. Shows a lot more rainfall variability and is quite susceptible to droughts and significant rainfall variability compared to other parts of Central America. This region is also very well known for many low-level jets in the lower troposphere. Many of them are topographical jets because the gaps in the terrains allow for the channeling of the winds through them. So Tuantepec jet, which is a northerly jet with a annual peak of about 8 meters per second, uh, and usually peaks somewhere between winter and spring, is located out here. The Papagayo jet with a annual peak of around 10 meters per second, again, is a result of the channeling of the winds through a mountain gap. And likewise, the Panama jet, which is again with an annual peak of 10 meters per second, peaks around winter and spring, is again a topographic jet. On the other hand, the Caribbean low-level jet and the Choco jet, because of thermodynamical and dynamical reasons, the Caribbean low-level jet is thought to accelerate because of the pressure gradient between the Atlantic high and the Pacific low, which causes the winds to accelerate. And likewise, the Choco jet also is in response to the system gradients and with that tremendous amount of diabetic heating from the orographic lifting level units. If we look at the annual cycle of all these low-level jets and cross-section of the winds from the European reanalysis version 5, you can see many of these low-level jets are low-level jets appearing in around 925 hectopascals. The Choco jet appears very closer to the surface. It is probably one of the weaker low-level jets among all these 5 jets. And so these jets are critical in terms of the intensity of rainfall and in the seasonal variability of rainfall across Central America. And obviously, these jets offer challenges to numerical modeling because you need models to be of sufficient resolution to at least permit, if not resolve, these jets in order to get the Marshall flux correctly in this region. The Central American monsoon jar is a region of broad, low pressure area that appears in the early part of the wet season and reappears again in the later part of the wet season with, with this broad region of low pressure area nearly disappearing during the summertime or during the peak of the wet season period. It often is attributed to spinning of tropical systems and also shoveling tropical storms from the Eastern Pacific into the Caribbean region as well. And again, the Central American jar, because of its variations, and is a challenge for numerical models to get them right. There is no standard definition to diagnose the start and the end of the wet season over Central America. Typically, the wet season or the summer season is fixed by calendar months, something like June to September. A variety of methods have been used. Most commonly, a threshold is used to determine when the start or the end date occurs. For example, Gramsci and Henry, 1972, using 124 stations across Central America, came up with the definition that the start of the rainy season is when the rainy pentad or the 5 year average rainfall reaches a threshold of 25 millimeters. And the end of the wet season is defined as the last pentad reaching the 25 millimeter threshold. They have developed isochrone maps, that is, um, the onset date maps of the evolution of the rainy season and the demise date maps based on these thresholds. But here I'm going to introduce a slightly different definition of the onset and demise based on a higher resolution data set that is available uh, temporarily at half hourly interval, which has been converted to daily interval. This is the NASA's Global Precipitation Mission precipitation data, which was launched in 2014 in collaboration with the Japanese Aerospace Exploration Agency, JAXA. GPM of NASA was the succession mission to the TRIM mission that started out in the late 1990s up to 2014. And the GPM has come up with now a consolidated gridded rainfall analysis available from 1997 to the present at zero point 0.1 degree grid spacing, um, which is, as I said, available at half hourly interval. But for this work, we converted that half hourly interval to 1 day interval and then use the data set. So before I go further about talking about the onset and the or the evolution of the wet season over Central America, I also want to draw your attention to some of the other features. We'll be relating the variability of the wet season of the Central American monsoon with variations, which is basically measured by the SST seasonally averaged over the Nino 3.4 region over the equatorial Eastern Pacific region. Then we will also relate it to the variations in the area of the Atlantic warm pool, which is marked by the 28.5 degree isotherm here. This is at the peak of the Atlantic warm pool, which usually peaks around early September. We'll also be trying to relate the variations or the evolution of the rainy season over Central America to the Eastern Pacific warm pool, which is again the area of the Eastern Pacific warm pool, which usually peaks around early May. That is when it has the largest area covered by the 28.5 degree isotherm in the tropical Eastern Pacific. And then we'll also be relating it to the North Atlantic tropical SST, that is between 5 knot to 20 knot in months of May, March, and April. So the way we define the onset date and demise date is pretty objective. We, at every grid point, define the climatological annual mean rainfall, which is a single number, and subtract from it the daily rainfall at that given grid point, where n is the number of days of the year and m is the year. And so you can develop this cumulative anomaly curve, and I'll describe this in a moment. So this is the cumulative anomaly curve on day I, which is summing up all the days up to day I in year M and subtracting it from the corresponding annual mean climatology for the grid point. So if I look at this graph, this is for a grid point over Nicaragua for the year 2009. The blue bars are daily rainfall in millimeters. The green line is the cumulative daily anomaly, which is basically starting out from January 1st of the year, and it keeps decreasing during the dry season, and then reaches a minimum, which is marked as the onset date. That's when the daily rain rate is exceeding the annual mean climatology for that grid point, and then it continues to climb during the rainy season, and then it begins to decline again when it reaches the demise state. So the minimum and the maximum are marked as the onset and demise date, as shown here. So the seasonal length is then defined as the number of days between the onset date and the demise date, and the seasonal rain is found by summing up the daily rain between the onset date and demise date. So as you can see, in comparison to the fixed calendar month seasons that is conventionally used in most um, analysis, uh, our wet season varies from year to year depending on when the onset occurs and when the demise date occurs. So we are accounting for the variations in the length of the rainy season or the wet season, which is important. A perturbation method akin to a bootstrapping method is applied to the daily rainfall data because we are diagnosing the onset and demise date at every grid point. Sometimes it is quite likely that we will be misdiagnosing the onset date because you could have random severe weather events that can cause a huge spike in the daily rain rate, which can force us to misdiagnose the onset date and likewise the demise date as well. And so the idea is uh, that we try to avoid such situations. So in order to do that, we develop an ensemble of time series, which is generated by shuffling the original time series on a time scale of 6 days, which basically is to desensitize the diagnosis of the onset and demise dates uh, uh, to uh, a specific rain event, severe weather event. So we do this perturbation technique 1,000 times for each year at each grid point. And so we develop a robust probabilistic estimate of the onset and demise date at every grid point for every year. So if you look at the climatological median onset date, which is based on Julian days. So day 110 is April 20th approximately, day 126th is May 6th, and day 130th is approximately May 18th. There are some very interesting features that appear on this map. You can see the onset is earlier along the Pacific coast than on the Caribbean coast, generally speaking. Um, the earliest onset dates, however, occur over Panama and Costa Rica, uh, and the latest dates occur over northern part of the domain, especially over Belize and parts of Nicaragua and Honduras. This progression is, however, not uniform, with earlier onsets occurring in the mountainous regions, especially along the dry corridor region. It's almost comparable to what you see in Costa Rica and Panama. There is also a west to east progression of the wet season onset as seen over here. As you can see, earlier onset occurs on the Pacific slopes line, and then as you move further eastward towards the Caribbean slope, occurs later. Likewise, if you look at the climatological median demise date over the 22 years, you see the earliest demise dates occur in the mountainous regions of Guatemala, El Salvador and Honduras in the Pacific coast. So the dry corridor region not only has an earlier onset, but also has an earlier demise. Um, and then the latest demise occurs in Panama and the Caribbean coast. So again, the Caribbean slope seems to have a later demise, just as it had a later onset. There is also a west to east progression of the demise of the wet season, as seen on this map. If you look at the climatological seasonal length, obviously the longest length of the season is over Costa Rica and Panama. and the shortest is in some of the lighter shade areas as indicated here. So this is pointing to the longer seasons. And there are also some long seasons out here, as well as out here in Guatemala along the Pacific coast, uh, out here along the Caribbean coast of Honduras. The shortest seasons are seen in Belize, parts of Guatemala here, parts of Nicaragua, and parts of Honduras. If you look at the seasonal rain, obviously the longer seasons have the highest amount of seasonal rain, but that is not always true because there are parts of Costa Rica and Panama where the seasonal rain is comparable to what you see in other parts of Central America. You can clearly see the dry corridor region out here, which is clearly depicted from the lighter shades. Um, Belize and the interiors of Nicaragua, Honduras, and Guatemala receive some of the lowest seasonal rain. If you look at the standard deviation, which is basically talking about the interannual variations, the onset dates have large variations, year-to-year variations. The dry corridor region, Costa Rica, and parts of Panama show very large standard deviations in onset dates compared to what is seen in Nicaragua. Um, the seasonal length has comparably less standard deviations in terms of days. Um, no, or I should say, actually, it's comparable, I should say, because the content was changed here. So it is quite comparable to the onset date variations. The variations in the seasonal length are contributed both by variations in the onset date and the demise date. And you can see here in the demise date variations, the Caribbean slope has far more variability in the demise date than the Pacific slope. And in terms of seasonal rain, Panama and Costa Rica are leading in terms of the variability, followed by parts of Nicaragua and parts of Honduras and El Salvador. Nonetheless, what this is telling you is there are some very strong gradients of variability, which again becomes a challenge for predicting. And so I sometimes feel that this is one of the biggest challenges for numerical modeling of weather and climate. If you begin to examine the local correlations, how does onset date correlate with seasonal rain and seasonal length or the demise date? We find that the correlations with demise date and onset date are pretty weak, as was Bailey stippling, which means that they're not statistically significant. So the variations in the onset date and demise date are relatively independent of each other. But if you look at the onset date and seasonal rain, there is quite a bit of statistically significant correlations of close to 0.6 or even higher, which is basically saying early onset leads to a better season or a later onset leads to a drier season. And likewise, there is a significant negative correlation between onset date and seasonal length, suggesting that early onset leads to a longer season and later onset leads to a shorter season. Likewise, if we look at the correlations between demise date and seasonal rain, there's a positive correlation over Costa Rica and Panama, which basically says later demise leads to more seasonal rain, and early demise leads to less seasonal rain. And demise date and seasonal length also show that along the Caribbean slope, there is a stronger relationship than along the Pacific coast, but nonetheless, they're all significant, suggesting that a later demise leads to longer seasonal length and early demise leads to a shorter seasonal length. And seasonal rain and seasonal length are positively correlated, basically suggesting that longer length leads to more seasonal rain and a shorter seasonal length leads to less seasonal rain. So these are local correlations. And one interesting thing about the relationship with demise date and seasonal rain is that largely concentrated between from Costa Rica to Panama, and the rest of the domain, it is rather sporadic. But if you go to looking at onset date and seasonal rain, the dry corridor is more strongly dictated by onset date variations. Um, while Costa Rica, parts of Costa Rica, the Pacific slope of Costa Rica is dictated by onset date variations, but large parts of Costa Rica on the Caribbean side or Panama in the last scale is not very strongly related to onset date variations. That is unlike the demise date variations with seasonal. If I look at ENSO teleconnections, the ENSO teleconnections with onset date variations is very weak. Likewise, with demise date variations, also the JJA that we refers to the seasonal mean of June through August, mean of 3.4 SST correlations with the demise date of the rainy season or the wet season of Central America is pretty weak. And therefore, the ENSO relationship with seasonal length is also quite weak. However, with the seasonal rain, it appears relatively significant along the Pacific slope and in parts of Guatemala. But in most other parts, the ENSO has a pretty weak relationship with the seasonal rain. One of the reasons why you see such weak relationship with ENSO is because ENSO seems to have a stronger relationship uh, during different parts of the rainy season. But when you look at the season as a whole in terms of seasonal variability, then the in-store teleconnections appear somewhat limited as indicated in this panel. If I look at the AWP correlations with the onset date, they again appear to be insignificant because they're statistically insignificant. And likewise with demise date, they appear very statistically insignificant. And if you look at the seasonal length, there appears to be a positive relationship only in some parts of Nicaragua and Honduras. And in terms of the covariability with the seasonal rain, there appears to be some negative correlation with rainfall over Costa Rica and Panama. So these large-scale SST variations seem to have very limited teleconnections for the wet season variations over Central America. And this is an example of teleconnections with the Eastern Pacific warm pole. Again, has somewhat limited correlations over the region. So in comparison to the local correlations with the onset date or with the demise date, they appear quite limited. This is the correlation of the seasonal rain with the North Atlantic, tropical North Atlantic SST as a whole in April and July. And you can see when it becomes almost contemporaneous with the summer season, the correlations become much stronger. But then in April, it is somewhat limited, but a bit more extensive than in connections or the Atlantic warm pool, or the Eastern Pacific warm pool connections. The point that I'm trying to drive here is the local correlations seem to be far more spatially extensive, far more robust, much more stronger, while these large-scale drivers have a limited teleconnection or a limited source of seasonal predictability for this part of the year over the Central American monsoon region. And so it becomes quite a bit of a challenge to do seasonal prediction of the wet season, given that the slowly varying SST variations has somewhat limited influence on the variability of the rainy season over Central America. So I'm not going to belabor the point of how we measure the probabilistic skill score here. I'll just leave it on the slides, the details on the slides here, and you can at your leisure read through these points and understand how we measure the probabilistic skill score. But in the next few slides, I'm going to be talking about how you can monitor the evolution of the onset date and then use the variability of the onset date to provide a seasonal outlook of the rainy season based on whether the onset date occurs earlier than climatology or occurs later than climatological onset date based on the local correlations that I've shown earlier. So because we have now an ensemble of 1,001 ensemble members, we can develop a probabilistic scale of what is the likelihood of a wetter season or a longer season or a shorter season and a drier season based on the variations of the onset date. What we will be measuring in terms of the probabilistic skill score is the area under the relative operating characteristic curve. And anytime this area is greater than zero point 0.5, then the forecast has some skill relative to a random forecast. And anytime the skill is below zero point 0.5, the forecast skill is considered to be useless or is not useful compared to a random forecast or climatology. So here are the pictures of the probabilistic skill scores as measured by the area under the relative operating characteristic curve for an early onset season. So based on the 22 years, we looked at seasons where there was an early onset and forecasted based on that, that the season would be longer. And in all these regions, you see the skill scores are upwards of zero point 0.8 or even zero point 0.9 in some locations, especially along the dry corridor, which is susceptible to large rainfall variations. And so just based on the evolution of monitoring the evolution of the onset, you are able to forecast usefully on whether the season is going to be longer or shorter. And likewise, if the late onset season occurs, then it skill improves even further in forecasting the shorter wet season. Likewise, if an early onset occurs, the forecast of a wet season appears to come right in many of these regions that have got scores of over 0.5 as shown here. And likewise, the late onset season continues to show a higher skill than early onset seasons. Uh, so if you look at, again, this is a repetition and basically there are some rare exceptions over Costa Rica and along the Atlantic coast of Nicaragua and Honduras where the scale appears to be a bit weaker than over the Tri Corridor region. So in conclusion, the Central American monsoon has a complex progression of a seasonal cycle of rainfall. Large-scale drivers like ENSO, AWP, North Atlantic SST have somewhat limited teleconnections or influence on the rainfall variability over this region, and therefore serve as a limited source of seasonal predictability, and which becomes a big challenge for numerical models that are used routinely for seasonal prediction over this region. The local relationships with the onset date variations suggest that the internal variations dominate the seasonal variations of the rainy season in the region. And across most of Central America, an early or a later onset date of the wet season is closely associated with a longer or a shorter and a wetter or a drier season, respectively. So these local relationships yield useful seasonal predictability for the Central American rainy season, as indicated in some of the previous slides here. And this is using no numerical models, is just by monitoring the observed evolution of the onset date, which is diagnosed by the minimum and the cumulative anomaly curve, that we can make a seasonal outlook for the forthcoming rainy season. I hope this short lecture will give you some insight into the climate of the Central American monsoon region, and you will learn more about the North American monsoon from the next speaker. Thank you once again for giving me this opportunity to talk to you.